Okay, so that's this problem. A three-phase induction motor having a synchronous speed of 1,200 RPM. The draw is 80 kilowatt from the three-phase feeder. And the copper loss and the iron loss in stator amount to 5 kilowatts. And the motor runs at the 1152 RPM. So we need to calculate the active power transmitted to the rotor and rotor I2R loss and mechanical power developed. The mechanical power developed to the load. And the windage and friction losses are equal to 2 kilowatt and the motor efficiency. So this has to be the calculated. Okay, so firstly we calculate for the active power transmitted to the rotor. So the formula is PS minus the iron and the copper loss. So this is the equation. So A is the active power transmitted to the rotor. So active power transmitted to the rotor, we can calculate this is the P0. Can we calculate? So this is the PS minus iron plus I square R log. So then input power is 80 kilowatt from the three-phase feeder. So this is the 80. And iron loss. The copper and the iron loss, the combination is the 5 kilowatt. So this is the combination of 5 kilowatt. So you got a 75 kilowatt. So power output is 75 kilowatt. And then we also need to calculate the slip. The slip is a formula, approximate formula, the S minus N divided by NS. So we can calculate the slip. NS minus N divided by NS. Okay, so NS, so synchronous speed. Synchronous speed only given the 1,200 RPM. So N is also the 1152. So we substitute 1200 minus 1152 divided by 1200. So by solving this one, we got a slip. That way 0.04. A slip is 0.04 we got. So this is for the active power transmitted to the rotor. And a B. We also need to calculate the rotor I square R loss. So rotor I square R loss, the formula is slip multiply and the P0. So this is the rotor I square R loss we calculate. Rotor I square R loss. Formula is slip multiply P0. So the slip we already know that slip is 0.04. The P0 we already calculated is a 75. So this is 75. So by solving this one, this way we get 3 kilowatt we got. Okay, so this is for the rotor I square R loss. And C, we also need to calculate the mechanical power developed. So C is the mechanical power developed. So mechanical power developed we can calculate. The formula given for the mechanical power developed is 1 minus slip multiply P0. So this is for the mechanical power developed. So Pm is equal to 1 minus slip multiply P0. So formula we write mechanical power developed. So this formula we use 1 minus slip multiply P0. Then we substitute here 1 minus slip is 0.04 and multiply P0. P0 is 75. So by solving this one we get 72 kilowatt. So PC. And the D. D means we also need to calculate the mechanical power delivered to the load. So in this case, given is a windage and friction load is 2 kilowatt. So after the mechanical power developed, we have to this is a mechanical power developed. You have to subtract the windage and friction loss, and you got the power delivered to the load. So mechanical power delivered to the load we can calculate mechanical power delivered to load. So the formula we use mechanical power developed minus friction windage law. Okay, we substitute here. The mechanical power W is 72 minus friction windage law 2, so equal to 70 kilowatt. And finally, we calculate for the efficiency of the motor. So that way, the final efficiency means mechanical power delivered to the load divided by electrical power supplied to the motor. So this is the efficiency of the motor. So we calculate the efficiency of the motor. This is the E. The formula we use the mechanical power delivered to load divided by electrical power supplied to motor. Mechanical power delivered to load divided by electrical power supplied to motor. Electrical power supplied to motor. So by solving this one, then we just can multiply with 100. So this is 70 divided 80 into 100. So there we get 87.5%. So this is for us we calculate for the motor efficiency calculation. We have to calculate active power supplied to the motor. So in this case, active power supplied to the rotor here. This power, active power supplied to the rotor. This power is sent to rotor, and this one is the iron and copper loss going out, and this one will be just so finally we use this is for the active power supply in the rotor. So iron and copper loss will be coming out. And then the mechanical power W by rotor means the active power supply minus the rotor copper loss. Then you based on the after that you got the sharp power and you will calculate the torque. So torque you have to use this formula. Here multiply 9.55 divided by rotor speed. Okay, firstly we calculate for the active power supply to rotor. Active power supply to rotor. So this calculation will use the active power absorbed from supply minus iron and copper loss. Active power absorbed from supply. Minus iron loss and copper loss. Iron loss plus copper loss. Okay, this one we can calculate. That will be the 40 minus iron loss is already given. Iron loss is the 5 kilowatt, and the copper loss is the 5 kilowatt. Iron loss is 1 kilowatt. So 1 plus 5. So 1 plus 5. So then we use 40 minus 6, so you got 34 kilowatt. So active power supply to motor is 34 kilowatt. And then we also need to calculate the mechanical power W by the rotor. So this we calculate mechanical power. W by rotor. So the equation we calculate is the active power supply to rotor minus rotor copper loss. So active power supply to rotor copper loss. So the active power supply to rotor is 34, and rotor copper loss is not given, so you assume 0. That way the 34 kilowatt. And after that, this is for the total power output. So this total power output you can calculate the torque. So you use the formula. PM equal to PM multiplied by 9.55 divided by 1 minus and rotor speed. So mechanical torque you can calculate. PM is equal to so PM multiplied 9.55 divided by rotor speed. So the PM we already calculated as 34 kilowatt, 34,000 multiplied by 9.55, and rotor speed is 900. So you calculate it as 361 Newton meter. So this is for the torque calculation. So this problem is 3-phase induction motor. The nominal rating of the 100 horsepower. And this is 75 kilowatt, and synchronous speed is one of the 800 RPM. So it's connected to a 300 4 source. So we use the 2 watt meter method to measure the 3-phase power. So total power consumption is a 78 kilowatt, and the ammeter measurement indicates the light current 78 ampere. The rotor speed is at 1763 RPM. So in this case, we also call the stator iron loss is 2 kilowatt, and weightage and the friction loss is a 1 by 2 kilowatt, and the resistance between the two stator terminals is 0.34 ohm. So those are the data we got. So stator iron loss is this is the iron loss at 2 kilowatt, and weightage and friction loss is a 1 by 2 kilowatt, and this is a 3-phase terminal. 3-phase winding resistance. So this is a 2 terminal means that we measure the motors resistance by this way. So this is a 3-phase winding here. So this resistance here we measure it. This is a 0.34 ohm. Then you will measure the resistance per phase. So resistance per phase is equal to 0.34 divided 2 is a 0.17 ohm. Okay, so we can calculate like this. Okay, so what you have to do is that input electrical power is only given as 78 kilowatt. So the input minus the power loss, so stator copper loss. But this is for the 3-phase winding. So the stator copper loss is 3I square R. So stator input power minus 3I square R, that's the power active power supply to the rotor. So can be calculated. So firstly we calculate the input electrical power is 78 kilowatt. Input electrical power equal to 78 kilowatt. And then stator winding resistance per phase is already calculated 5.17 ohm, and we calculate stator copper loss. So stator copper loss will be 3I square R. So then you calculate the 3. The stator current already given as 78 ampere. So this is a 78 ampere. And resistance is a 0.17. So by calculating this one the 3.1 kilowatt we calculate. So this is a stator copper loss. And then the electrical power supply uses a rotor. So there are 2 losses. Stator copper loss and iron loss you subtract, and the active power supply rotor we got. So total power input is 78 kilowatt, the minus the copper loss and the iron loss. So you have to subtract the iron copper loss and iron loss. So in the problem, if the stator iron loss is given at 2 kilowatt, and stator copper loss we already calculate the 3.1 kilowatt. And therefore we can calculate this active electrical power supply rotor can be calculated. So this is the electrical power supply rotor. So this formula is the input power. Input power minus iron loss plus copper loss. So then we substitute here. Input power is 78 minus iron loss. So iron loss will be 2 plus 3.1. So then we 78 minus 5.1. So you got that 64.9 kilowatt. So we got like this. Okay, so this is for the first thing we calculate. And second one means we also need to calculate the rotor copper loss. The rotor copper loss. The rotor copper loss is the we can use by the formula. The rotor copper loss is a slip multiply the stator copper loss we got. So this is the equation we can calculate. Rotor copper loss is equal to slip multiply the rotor copper loss is slip multiply P0. So this is the equation. So rotor copper loss you can calculate slip multiply P0. Rotor copper loss, slip multiplied P0. So P0 we already calculated. The electrical power supply to this rotor is, this is P0. So this is a P0. So how to calculate the slip? Slip formula is slip is equal given as ns minus n divided by ns. So this is slip. Slip is a s. So that will be the ns minus n divided by ns. So this is a slip equation. So in this case, we already know that ns is 1,800 rpm, and the slip is a 1763. So we substitute 1,800 minus 1,763 and 1,800. So slip will be 0.0205. And then you can calculate rotor copper loss. Rotor copper loss. So then we slip is 0.0205. Minus P0 is at 64.9. Then we calculate this will be 1.33 kilowatt. So this is for answer 2. The rotor copper loss can be calculated 1.33 kilowatt. And then we also need to calculate the shaft power. Shaft power means the input is a mechanical power develop. So we have to calculate the rotor copper loss. So at the added power supply to rotor, we only calculate 64.9, and rotor copper loss we subtract. And then this is the mechanical power output. So we got. So this mechanical power output, you also subtract the windage and friction loss. Finally, you got the shaft power. So then, firstly, we need to calculate the mechanical power developed in the rotor. So PM, mechanical power. In rotor. So this is the PM. Minus rotor copper loss. So the P0 is 64.9 minus 1.33. So then you got a 63.5 kilowatt. So mechanical power deployed in rotor is 63.5 kilowatt. And after that, the shaft power. Shaft power is a mechanical power deployed in rotor. And as I said, we already calculated. And we need to calculate the windage and friction loss. Finally, you got the shaft power. The shaft power is PM minus friction and the windage loss. So we calculate shaft power. Equal to PM minus friction and windage loss. So then we substitute here. So this is the PA 63.5 and minus friction and windage loss is the 1/2. So we subtract this with the 63.2 kilowatt. So this is for the shaft power. So shaft power you got. So in this case we already know the input electrical power and the shaft power. So shaft power is final output, input electrical power is the origin sub input. So that this ratio will be you can calculate the output power. So output shaft power is with this one you call in a kilowatt unit. So you divide it by you multiply with 1/34. Then you got the horsepower. So we got the horsepower. The horsepower is equal to 1/34 into kilowatt. So then 1.34 multiplied 62.3. So you got the horsepower. Then we get 83.5 horsepower. So motor horsepower is 83.5 horsepower. And so only final step we need to calculate the efficiency. So the shaft power is at 62.3 kilowatt. The input electrical power is at 78 kilowatt. So then we can calculate the efficiency. So then we calculate the efficiency. Equal to shaft power divided by input power multiplied by 100. Okay, shaft power we calculate is at 62.3 kilowatt and input power is 78 into 100. So then we calculate this one with the 79.8%. Okay, so finally we also need to calculate the torque. The torque formula we here given. Torque is equal to PM multiplied 9.55 and the rotor speed. So rotor speed is in the problem already given the rotor speed. So 1763 are RPM, and the PA is here the one with the sharp power we calculated. And so we substitute 62 by 3. And so this is where sharp power is this rate. This is the sharp power. Okay, so sharp power we can calculate. So 62 by 3 into 10 power 3. 62 by 3 sharp power. So PM multiply 9.55 divided by 1 minus S into NS. So this is so this sharp power is a combination of the both input. So this is the sharp power equation. So PM multiply 9.55 into 1 minus S into the synchronous speed. So this is for the this is we can calculate this. This is for the torque. This we can calculate for the torque. Torque equation is PM multiplied 9.55 divided by 1 minus S into NS. So the PM we calculate the PM already is 63 by 5 into 10 power 3. We convert it to the watts. So the 1 kilowatt is 10 power 3 watts. So we multiply with 10 power 3. And multiply with 9.55. And 1 minus S into S is 1763 RPM. So that one will be the 344 Newton meter. So this is the answer for this problem. And similarly, this one I also give you the practical aspect. So